Welcome back, guys, to part two of our conversation with Matt. We're just gonna continue.
Yeah, so before we stopped, or before in part one, we were talking about the difference between two of our courses at University of Toronto, 137 versus 237. That's our first year calculus and second year calculus courses, respectively. So, Matt, maybe you just want to finish up on the topic, the main difference between the two.
Yeah, for sure. I mean, as Ray said, they offer the university offers like series, in which case you can take the 235 series, which is going to be a dedicated calculus course, which is in the sense that it's just the machinery of calculus necessary to apply to some statistics, apply to some optimization problems, apply to some physics, apply to some, you know what I mean? The 237 is going to be calculus and analysis. So you're going to get into the construction of these objects from like a rigorous standpoint, but then the course also emphasizes like applications. Whereas then we also offer 257, which is just analysis 2, which is basically only the rigorous construction, not that many applications. But what I was just saying before is just I strongly recommend 237. Not only use, because once again with 237, you don't only get the rigor, you get it's like kind of the perfect in between. You get a lot of application that helps you so much with a E&M. I can't even like explain it. Like PHY 250 is all multivariable calculus, surface integrals, volume integrals, like path integrals, all that stuff. And
If you don't mind me asking, what did you get in the course?
yeah, I got an 85.
In 237?
No, in 237 I got a 91. In 50.
What?
What?
Yeah. Yeah.
Holy.
Oh,
Yeah.
my, okay.
Yeah. That's okay. There's another inspo for you guys if you want to hear it. Like, once again, came in, did not have good marks necessarily, and my first course is probably like a B- average, and I killed myself for a B- average in first year. And then this semester that just passed is when I earned my first proper 4.0. So where PHY 250 was my lowest mark, being the 86. So if you get it, just grind. Just grind.
Wow.
Grind.
Wow, that is
that is very inspiring.
Yeah, I'm just saying it should be, you guys. I did way worse than you guys. You guys are definitely like...
Yeah, but you ended a lot higher.
I mean, you'll get there. You'll get there. It took me a
soon.
Yes, I'm confident you guys will be just fine.
So I guess I want to start out this part two, if we're just starting to talk about it, with just talking about physics and math in general, right? So like maybe some future concepts and stuff. So something that I think a lot of people are looking into right now, and a lot of people are saying could be the future of, computing and stuff, is quantum computing, right? Yep. So what are your opinions or ideas on it? You think it's possible? Do you think maybe one day we can get a quantum laptop? You think that's a possibility? What are your thoughts?
It's fascinating first and foremost. It's kind of mind blowing. It's almost scary. It's like, especially I don't know how much the listeners kind of like are familiar with like the capabilities of these machines, but it's just absolutely insane. But in terms of like the physics behind it, it's also fascinating. And I do think quantum laptop, I don't know if I'm knowledgeable enough to give a time frame on something like that at all, but I think the possibility of these devices is like so incredible. And I think the math and the physics that underpins them is incredible. Like the linear algebra that goes behind the programming of these things, and even just on a pure like computer science level.
Are you interested at all in computer science? Like, do you code in like your spare time and stuff?
I was actually thinking I'm still considering potentially doing a computer science minor.
Yeah.
I'm taking 108 and 148 and maybe 165, but in practical physics, which is I believe it's PHY 204. I don't know exactly what the course code is, but you'll take it first semester, second semester next year as specialists. You do a lot of scientific programming there. So I've done a lot of Python over the last 2 years, and it's really interesting, but I don't have a direct love for it as a field in itself. Like my friend actually asked me this exact same question, and he studies like liberal arts, and he's like, how do you love computer science in and of itself? And I go, people can do computer science as an art, right? You can absolutely just get really theoretical with it and, you know, do a lot of really cool stuff and not necessarily need it to be applicable. Just like math. You can do a lot of math that's not applicable in like a direct sense, right?
I
True.
guess that, yeah, I guess that is actually true.
Yeah, and I view it like this. I view the computer scientist, this is like kind of ad hoc, since hopefully no one like shoots me for my opinion, but at least how I take it is the computer scientist is like the guy at the body shop. You can build an incredible car and it can be beautiful and it be aesthetic and be useful and whatnot, but to me it's still a car and it drives, right?
Hmm.
Yeah.
Do something. You press run at the end of the day with that code. Do you know what I mean?
Yeah.
To me, the
Yeah.
math is like a painting. It's art for the sake of it. Do you know what I mean? And I'm more
Hmm.
like that personally. You know what I mean? Like when I'm doing,
True. Yeah.
I can love it. I can be deep in it. It can look great, work great. But to me, it's still a car. I still just want it to output the physics that I'm doing, and the physics is the painting, and so is the math. Do you know what I mean? I find it
Yeah.
a bit more pure of an art than the computer science.
True. Because there's something really like not primal, but like just nice, I guess,
Yeah,
about like picking up a pencil and just writing math, you know?
yeah, ideas straight from your. It just you're like yanking thoughts. You know what
Yeah.
I mean? Same with the comp sci, but at the end of the day, I still view the comp sci as more functional. But it's artistic. Don't get me wrong. But to me, it's more functional art, like a car.
Hmm.
True. I agree.
How about we just talk about like what you guys are really looking forward to learning in the coming year or so, and I can kind of just like add my perspective, having done quite a bit of what you guys are
Sure.
doing.
Okay. Okay. Sure.
Yeah, I'll go first. So I'm really excited to learn about like Maxwell's equations and things like that. I like my favorite. I've said this before. Like my favorite unit was like E&M, definitely. So I'm really excited to take like a course that's completely dedicated to that.
Mhm.
And in math, I am super excited to like do analysis. Like I just want to get to an analysis, but I feel like I need to learn a lot more before I get there.
Okay. What about you, Ray?
For me, I'm actually incredibly excited for quantum mechanics.
Mm.
I think I've said this many, many, many times, and I'm very scared. I'll tell you that
Okay.
because I've heard all the terrible stories with, oh, I got a 25% in my third year quantum mechanics course, stuff like that. So I'm equally nervous, equally excited, but I think that's definitely the course or topics I'm most excited about because I've just always been excited and interested in particle physics and how the fact that physics on a quantum level is just so dramatically different from physics on a classical level. I just found that interesting.
Yeah. So I could just kind of touch on each one separately. So first with the E&M, that's a really good what's it called thing to look forward to because E&M is perfect. I don't know how else to describe that. Like it is the way it's been formulated right now and the way we express it, the language, it's so self-consistent. It's one of the best physical theories we have, at least on the level
Wow.
you're about to learn it. Not quantum E&M or relativistic, which is also damn near bulletproof, but the one that you're going to be concerning yourself with in the next year is like so well put together, and it just feels so. It's going to be one of the first like how do I word this? You know how for the past 2-3 years of your physics life, it's kind of been maybe felt a little cut and paste in the sense where you go, okay, now we're in rotational motion, and now we're kind of in special relativity, and now
Yeah,
and you're kind of just putting it all together in like kind of this collage sort of thing. E&M is going to
true.
be the most complete picture that you've seen to date. It's gonna you start from like the complete ground up where you define force fields, then you generalize it to an electric field, and then you define energy and you define charge as opposed to mass to be the substance or the quantity that interacts with these fields. And if you go real slow with it, it's going to feel like the first time you just it's going to feel a lot like you're inventing this physics. Like you get to see it happen from like ground zero. You know what
Wow, that's incredible.
I mean? With any preconceived anything. Where like even in grade 11 physics, you understood like rolling a ball. And you go, oh, it would move, and you had preconceived notions. This one's gonna feel like from like scratch. Do you know what I mean?
Yeah,
So
Oh.
yeah, you're gonna really, I think you'll sink your teeth into it. It gets complicated. Don't get me wrong. It's not like it doesn't have its like trickiness to it. You'd be like, oh, why is that true and stuff like that. But it's in terms of its axioms, it's so fundamentally sound. Now, quantum mechanics, on the other hand, we all know quantum theory is one of the most well-tested theories in physics, in modern physics, and it's really confusing, but it is still very self-consistent. Like it predicts accurately and whatnot, and you know
Mhm.
it's good. Like it's really solid. But the way it's quantum mechanics is one of those things that there's no good way to get started. It's just like, at least from what I know, there's it's not going to feel as holistically like nice as E&M does. It's going to be more like, okay, you've lost me.
Yeah, I remember when we started our quantum mechanics unit, he just pulled out like the wave equation. I'm just like, wait, hold on. Give me 1 second before we start this. Like, yeah.
They'll start you off with like basic probability theory. So like, the wave function as a probability density function, or well, not the wave function, but its amplitude squared or its modulus, which I'm sure you
Yeah.
guys are nerds. You definitely all on those YouTube videos, and you've seen like psi absolute value squared and like all that stuff before.
Yeah.
I can say these things like passing without you guys being like completely like, what is he even talking about?
Mhm.
But
Yeah.
they'll introduce it probability as a probability, really is what it is. And then
Everything will pretty much be a probability, right?
initially,
In that
initially,
course.
and then it just kind of all falls off the deep end, at least for an intro quantum course, because then they get into Hilbert space and what these wave functions actually are as vector objects in a Hilbert space, and then that's when you need a lot of linear algebra, and then that's when we get into the really fun discussion: is how much math should you learn before you do any physics? And me and my friend have like talked extensively about this, and we have our own opinions, and I want to get you guys's. But at least for
Mhm.
me, I'm like, man, I don't even know because
Yeah. It depends how much you want to know about physics,
exactly,
I think.
and how theoretical too.
Yeah.
Applied physics, I think
Mm.
you can get away with a bit more, but yeah, go ahead. Right?
I think the really interesting thing about physics, and this is something that I've noticed for like a long time, is that very, very, very simple concepts are actually like not that simple if you really go on a deep physics level. Like for example, as you were talking about a rolling ball, right?
Mhm.
It can seem so simple if we're doing it in grade 11 physics. But
Yeah.
let's say we have like a rolling ball example in second or third year university physics, it'll
Mhm.
probably be with like a bunch of things,
Mhm.
right? So analyzing the same situation with more physics knowledge, I think just requires more math knowledge because to go to that, because every physics concept, or at least I think this, that
Yeah.
every physics concept can be made harder just
Mhm.
by including more math. Because I think the perfect example is F equals ma, right? Like you were talking about how that's just an ordinary equation, but if you were to dig deeper, you see that it's a differential equation, and then you can just keep piecing things apart, you know? So I think that's really cool that every single topic can be just made 10 times harder if you include more math in it.
Yeah. 10 times harder, but also 10 times more in depth.
Yeah, true, true.
Like once you actually like it was like for example, I think this will excite you because it excited the shit out of me when I did it in second year, which was like, remember in high school when they would just give you the projectile motion equation,
Yeah.
Yeah.
or pardon me, or the trajectory equation? It was that big
Mhm.
ugly one? That big like where it's like, do you know what I'm talking about? The trajectory
But
equation where
like for the distance on the ground?
no, it's like y is a function of x, so it just gives you the height as a function of its like horizontal position.
Yeah.
Okay, yeah,
We've
yeah,
seen those. Yeah.
yeah.
It's really big and shitty. When you actually start getting to understand F equals ma on an ordinary differential equation basis, you get to actually start solving it and manipulating it and derive all these kinematic formulas you were given. So like x equals x naught plus v naught t plus half at, all that stuff.
Yeah.
These things literally unfold in front of you if you just know that it's a differential equation and you know how to solve differential equations. It's so crazy. It was like the first time in my life where I was just doing a problem and I was like, oh, I just stumbled upon the trajectory equation.
Yeah. I do
Mhm.
find that super satisfying. Like when you see an equation like in grade 11 and then you get to the point where like you can just like go to the origin and derive that
Mhm.
equation, and it's like, wow, like I know a lot more than I used to know.
Oh yeah, every single one of those kinematic equations, you'll just you'll be like, of course, that's how it'll feel. It'll be like, why wouldn't it be?
Mhm.
Yeah.
And like
Even E equals MC squared, when we derived that, I
Mhm.
was so satisfied, like very confused. I'll tell you that. I was extremely confused, but I was so satisfied that I had finally known the derivation of special relativity, one of the most famous equations in the world. Like, that's a very satisfying feeling. So I definitely understand that.
Yeah, yeah, for sure. Even the derivation presented then, correct me if I'm wrong, it was more so a physical argument they gave, like the setup at least.
Yeah.
You know what I mean? It kind
Yeah.
of like, okay, let's consider something moving like this, and like, you know what I mean?
Hmm.
It was a physical argument they gave. When you get later, the more math you do, and if you stay in like a physics spec and whatnot, you'll see it derived from a math perspective, and it's equally as fascinating. It's like more. I have a linear algebra textbook on my shelf right now that has a subsection of chapter 9 just called the special theory of relativity.
Oh, damn.
Mhm.
They break it down just on a linear algebra level, where they just go, x, y, z, t,
Yeah.
a
Yeah.
position, space, and then a time coordinate as well. So
Mhm.
that's a four tuple of real numbers, of course. So it's just an element of R4, which is a
Hmm.
four-dimensional Euclidean vector. I don't know how have you guys taken 223?
Yeah.
Mathew?
Yeah.
Yeah, yeah. So you're following me at least.
Yeah.
Yep.
You can then just view some like a particle space-time coordinate as just an element of R4, and then you can start applying. You can think about what does it mean like for what is the span of a space-time coordinate? What's a subspace what in terms of these in terms of a physical sense, you know what I mean? And then space
Mhm.
time is just you know a kind of an well, I mean, I don't want to speak wrong and then have someone it's a topological embedding within, it's a differentiable manifold with like a Riemannian metric. It's like a very fancy thing, but the point is
Yeah.
four-dimensional space, right?
Hmm.
You have an x, y, z, and a t. So like even the reason why I kind of brought that up is just it's so interesting how you can just go so much more into it when you have that math.
Mhm.
True. Have you taken 224?
Yeah,
How did you find that?
it was great. It was the first time you get to generalize a vector from just a Euclidean thing, so like a tuple of real numbers, right? Like
Yeah.
y, z, t, or w or whatever, like x1, x2, x. And then you go, no, a vector is just an object. Like a matrix is a vector. That might sound
Yeah.
insane to you now, but it is. And so is a function. Like certain functions, you can define a vector space on, like the set of all continuous real valued functions is a vector space. And you can add continuous if you do, you learned this in 137. You take the sum of two continuous real valued functions and you get a continuous real valued function.
Yeah. Yeah.
Yeah.
That is very similar to how you can add two vectors and still get a vector in the vector space. So that's
Oh, that's true. I never really thought of it like that.
you can take a product like f times g, and they're both continuous and real valued, and once again, you get a continuous and real valued function. So there you go. It's closed under products as well. So that's a vector space in and of itself. So you get to generalize these ideas and go, vector is just a word. Vector is just an object. It's not an arrow. It's not like do you know what I mean? It's just a
Yeah.
set of objects that satisfy specific axioms, which are vector space axioms. But the point is, all this generalization of math lets you generalize physical reality because physical reality is very weird, of course.
Mhm.
Like, for example, next year I'm taking APM 426, which is general relativity, but applied in a math perspective. So you guys, if you stay in the physics spec, you'll take, I think it's like PHY 483 or something, which is general relativity, but the physics course. So it's a PHY, but they also offer a general relativity from a math standpoint, APM, which is applied math. So
Oh.
it gets to a point where you can approach these subjects completely on a math side or on a physical side. Do you see what I'm saying?
Yeah.
Yeah, that's actually pretty interesting.
Yeah, like you can view in the physics side, you can kind of study space time and all of its crazy
Mhm.
from a physical standpoint, or you could view it on the math side and go, oh, this is just a manifold, and we can do all these things with it and unravel like super theoretical and like prove all these different things about it. And but yeah, it just harkens to the fact that the more don't be scared of the math. The math literally makes your physics exponentially better. You get a little inch more math, like you get or differential equations. Now F equals ma is like explodes in possibilities. Do you know what I mean?
Yeah.
Yeah.
It's just like the
Okay.
smallest
Mhm.
math takes your physics like tenfold forward. You know what I mean? And
Mhm.
then if you get even more math, your physics just like explodes. That's what Einstein had to do to even get general relativity. He had to work for like 10 years with different
Yeah.
mathematicians, differential geometers, and like these guys to go like, hey, like I I posit that this is kind of like the nature of space time, but I can't write it down yet. Like I need you guys to, you know what I mean?
Right,
Yeah.
he had to learn the language of math
Yeah,
to be able to translate his ideas.
yeah, absolutely.
So we were actually talking about dimensions, I think, a bit before, and I had a really interesting question, or at least that I thought was interesting. How
Hmm.
many dimensions do you think are possible? I'll say. And the main reason I posed this question is because the next question I was going to ask was going to be whether you think, string theory is a possibility, and
Um,
how they posit that there are 10 dimensions, three of which we can see and live in, and the rest are pretty much microscopic quantum dimensions that are kind of like wrapped up into one another, right?
right.
So I guess the question that I'm trying to ask is, do you really think there can be more than like 3 or 4 dimensional space than we can see now? And do you think that it's like, what's the word for it? Like quantized? Do you think that these dimensions are quantized?
Okay. Um, so first thing, I want to be really careful when we say like wrapped up and kind of like
Yeah, I didn't really define it properly, but I'm just trying to give a loose, vague description.
it's just like on in very high level maths they will use words like nested and
Hmm.
wrapped up, and it doesn't, and the reason why we do it is because physical things make sense to our human brain, so we like take really abstract things and use normal words to describe them. Do you know what I mean? Like the thought
Yeah.
of a dimension being nested is more like it's more of a mathematical abstraction than it is than it is for like your average person to hear someone say like a microscopic dimension and think like
Hmm.
a subset of space is somehow smaller than another one. So like I first just want to like put some clarity on that, so that way it doesn't sound like like pseudoscience.
Yeah, yeah, yeah.
Yeah, so just for like listeners and stuff, like in that respect, just to answer the question directly, yeah, I'm positive, which is such a ridiculous thing to say because I'm no Nobel Prize winner. There's got to be more dimensions than we interact with, because like you said, string theory posits somewhere like 10 or 11, um
Hmm.
and what's it called, general relativity posits around basically 4 because we just add time as that extra dimension. And even when we say the word dimension, we don't even mean it in the normal Euclidean sense where it's like just one extra axis. Like when they're talking about string theory, it's like the concept of dimension gets generalized too because it's so mathematical. It's not just like more space to move into. It's like a different thing, even like in and of itself. It's like
It's a very confusing concept.
it's hard to even for the amount of math I know. It's still like it still pales in comparison to what they're really getting at, like the really deep topology and like the really deep differential geometry and all that. When I think of just like on a sort of philosophical, sort of like we just like talking about physics level, I go, okay, if the space let's just go Einsteinian, the space I'm moving through and the time I'm moving over, I guess I could say,
Hmm.
if that's described by this four-dimensional manifold space-time, then there's clearly things going on that I just am not being able to observe that must be going on. Do you know what I mean?
Hmm.
Same,
Hmm.
Yeah.
you could take like the classic example of like the ant on the ball, and he thinks he's on a two-dimensional thing, and we're like, no, you're obviously on a sphere. You know what I mean?
Hmm.
I think
Yeah.
we're the ant in so many respects, where maybe another being could very clearly see like, oh, of course, like space time is malleable in these weird ways, like for example, gravitational waves to certain beings might be just as obvious to us as water waves. Like
Yeah.
I think there's so many things that's where you can have the great question of like when you're doing math and you're and people are generalizing and generalizing and generalizing, and you're like, okay, how much of this is real, quote unquote? Because
Yeah.
I always ask myself that. I go like, are we doing math for shits and giggles here, or like, is there? I always want there to be some sort of application, maybe. Do you know what I mean?
Yeah.
Like, what's really like going on? And so, in that respect, you can generalize and generalize and generalize. And we've all heard this classical thing where it's like someone solves a problem in pure maths, and then 40 years later, that describes a physical phenomenon perfectly. But
Yeah.
at the time, it was just this ridiculous fact about 12-dimensional spheres. Do you know what I mean? I find it
Yeah.
kind of a coincidence that all this math that seems ridiculously abstract to us but works. Like, okay, quantum mechanics is the best example. The math is like so dense, so theoretical, so abstract. It's not something we experience on an everyday basis, but for some reason it's predicting things. You know what I mean?
Hmm.
It's like if the ant just somehow started thinking harder and harder and harder, and he goes, no, well, actually I'm on a 3D thing, even though I can't see the 3D thing. The same way we're in this 4D space-time, we don't see this fourth time dimension in like a spatial way. You know what I mean? So in that
Hmm.
respect, that's why I do genuinely feel, and I feel like all of us do, that when we're doing this physics and this math, we're peeling back some layers of reality that we don't necessarily get to interact with directly, but we're figuring it out. You know what I mean?
Yeah, that's one of the main reasons why I started going into math and physics is because I'm so interested in like what is actually happening and how much I
Yeah.
can actually know. Because there's definitely there's more things that I don't think humans will ever be able to know than things that we know now. I don't know if that made sense, but yeah.
I think the entire concept of physics is just a baby asking why. Like, I'm not even joking. I think that's the entire concept because the entire notion of science started when people started asking questions, right? And the question predominantly being why. Like, why does this happen? Why does that happen? And the problem with science, or not really problem, but the challenge is that the moment we answer one question, there are 10 more questions on that answer,
Yeah.
right? And that's the entire reason why I don't really think we will ever truly know everything, because anything that we say or prove or answer, we will have 10 questions for that answer. So it'll just keep going on in this exponential sense where we'll really never figure out truly every single answer in the universe, but we can obviously try to get as close as possible.
I completely, yeah. Like, just to piggyback off that, like, it's such a, it's that's really just the nature of science, right?
Yeah.
And that's why, you know, that's why you can also get into the debate of like, is math a science? And personally, I don't think so, because math, you don't do an experiment. Really, that's it. Do you know what I mean?
Yeah, that's true. That's true.
You can introduce a new mathematical object, define, and you can define things, and then you can see what corollaries come about, and that's what math research really just looks like. But I don't. It's not necessarily, like physics. You actually have to go out and you describe observation. You know what I mean? Math and
Mhm.
physics is like, it's kind of like, in math you set up the world and then you play within it and you see what's going on. And then physics, you're given that world and you're trying to work backwards. So like math, you set up the axioms. It's like sandbox mode. Do you know what I mean?
Yeah,
Yeah.
yeah, yeah.
You define what you want a function to be. You define set theory. You define, like, everything of math is just defined by humans, right? So then you get,
Mhm.
is it math discovered or is it invented? And it's probably more so invented, but the fact that it's describing so many things in physics which are completely discovered makes it seem like you're discovering math at the same time. But I'm not exactly sure if we are.
Mm.
You
I
know
was
what I mean?
actually going to just ask you that question if you think math is discovered or invented.
Yeah, I was listening to another podcast with Three Blue, One Brown,
Love it.
and he said something that was super interesting. He said that um like math works so well in our world that it kind of feels like it's a discovery, that you're discovering something. But at the same time, um like a world where simple mathematical descriptions aren't possible could not, like that kind of world could not support intelligent life,
Mhm.
which is like a super deep statement, because if you actually think about it, it's super interesting, because if you can't describe things simply.
Mhm.
And like let's say like F equals ma was just super incompressible
Right.
and super very very difficult to uncover, I guess, then maybe that world is just not fit for it being discovered,
Hmm.
if that makes sense.
That's a
If
cool
you
take.
can't explain it simply, you don't know it well enough. Albert Einstein. Sorry, I just heard can't explain simply, and I just thought of that quote.
Yeah, I mean, he definitely didn't go. His idea was far from the simplest take, I think, which is kind of he kind of like just shook the world up when he dropped those papers, and that was
Mhm.
a stretch. And I can't wait to have this type of conversation with you guys again in a year, where you just have like
Yeah,
more perspective on the math that like kind of underpins all this stuff and even more of the physics. And then you know what I mean, and then a year after that, do you know what I mean? It's so crazy how much info's stuffed in our brains over the course of like 4 months. Like,
yeah,
it's insane.
very true.
Like, the
Yeah, it's
amount
actually crazy. Yeah, I definitely understand that.
you're about to learn in the second year, it's like
Yeah,
so
I'm excited for it though.
I'm so excited.
everything that you understand right now is just going to get generalized so much. Even I heard you guys talking about moment of inertia on that last podcast. Like, even that concept, once you get to 354, once again, that's the third year classical mechanics course. You formalize in the language of tensors, which are,
Oh yeah.
and I'm sure you guys have heard that before. Like,
Mhm.
Yeah,
you can have moment of inertia vector where you just associate the position with it as well. Normally, what we do is we integrate to find the magnitude of it. That's where you always get a number like 1/12 mr squared or whatever.
yeah.
Yeah, but you can also express it as a vector quantity if you want. But anyways, you can generalize those to tensors, which are like you know what a matrix is. You guys both know what a matrix is. It's kind of
Yeah.
like,
Yeah.
once again, for all listeners, I should have just like ad hoc everything right at the beginning. I'm speaking super hand wavily about a lot of stuff, and please don't. I know I got friends with the rigor. I get it. But we're shooting the shit right now. Okay, we're having a good time.
Yeah.
But for example, a tensor, like you know what a matrix is. Now add a third dimension to the matrix. So make it a cube. And now,
Oh.
like, I bet you never thought of that. You know,
No.
the same way you can put entries in a matrix, you can make like a Rubik's cube where each little box is an entry in this tensor, as opposed to a
Mm.
matrix. And then that can describe things as well, and like blah blah blah. I'm not super knowledgeable on tensor calculus. It's more like fourth year real analysis or maybe even third year, but blah blah blah. That's once again rigor police. Please don't shoot me.
Mm.
We are pulling up on 34 minutes now. Um, should we just end it here?
I think we can end it. Yeah, I think this was pretty good. Once again, Matt, thank you so much for coming on the podcast. It was really great having you here.
Yeah, man. I had a great time. This
Thank
was
you. Thank you.
super fun. And once again, like, this is just what, for everyone listening who's like maybe not in this stuff completely, which I doubt you made it this far if you're not into this stuff completely,
Yeah.
or your partner's girlfriend. It's one of the two. Um, this is just kind of like what we do. Like, we talk, like, for fun, and this is a blast for me, guys. Once again, thank you, because like I said, we don't get the opportunity to do this type of stuff enough. You know what I
Yeah,
Yeah.
I know.
mean? Especially
Just
with,
sit down and talk about math and physics.
yeah, and just like get to be fascinated about it. Like this, like I said at the beginning of the podcast, like the same way most people can just sit down and like nerd out about things they care about, art history,
Yeah.
politics, sociology, things like that. And I like that stuff. I get down with that stuff, but I love that we're taking the opportunity to nerd out about things that are less accessible than just talking about art.
Hmm.
That people are seeing that you can do this, and that we can kind of like promote this idea of science communication and math communication even further. Because I think it's something that everyone has a natural fascination with. Like, you can't put a toy in a baby's hand and not have them freak out. You know what I mean?
Yeah.
Or like
Yeah.
do anything physical or scientific and stuff like that. And I think you guys agree. And honestly, maybe next time we can talk about math and physics education and the issues with
Sure.
it.
Of course.
Yeah. Yeah.
Cool. because it's something I'm passionate about. But
I was actually going to ask you a question about like how would you, teach science to youth and stuff like that. We were actually going to have like that kind of talking session, but maybe next time, maybe part 3.
yeah, I think we should definitely like have that as a talking point
Yeah.
for another.
Yeah, man.
But just like what I was saying, it's just I love seeing dudes like Neil deGrasse Tyson. We all love him, idolize him. He's a beast because
Mhm.
Yeah.
open about his science communication. He doesn't buffer it with all this terminology that's too hard to follow. And majority of what you can see in his voice and his face is just passion about it. And that's what really speaks to people. And that's what's going to make people tune in and like care and be like, oh, maybe I kind of like that stuff. And
True.
Mhm.
I want, that's why I'm super in support of this because it's like, hey, we get to come be us right now, which,
Yeah.
Can't
and
really do it on a daily basis.
yeah, like everyone I've talked to, they would think like, oh, dude, like, and we all get this stereotype. Oh, you guys are smart. Like, yeah, great. Like, love to hear it, but whatever. But and, it goes well with the parents. It goes well with like, oh, like your aunt. Oh, I study physics and math. Oh, that's so great. That's so great. You can't hear it. You know what I mean? You get like,
Yeah.
but you don't get to actually like, share it properly.
Yeah.
Unfortunately, yeah.
I think these things are the best, like open form, free flowing, just talking, nerding it out.
Thank you so much.
Yeah.
Yeah.
That's the point. That's the whole point of the
Yep.
podcast.
Yeah, and just spark interest in like just anyone listening, and because it's really the same way dudes will get around the table and talk about politics. This is just guys being dudes for everyone listening. This is the best way I can put it. This
In
is just
our field, this is exactly what guys do.
this is what guys being dudes looks like. Okay, if you're around the table and there was a couple beers out, it would be as basic as any other type of get together. But once
Yeah.
again, just huge shout out to you guys. Love to get back on it. This is really cool that I got to be the first part tour. I feel like our
Yeah.
podcast got to do like 6 hours or something crazy.
Yeah.
Like,
Well, we're making history right now. So yeah,
Yep.
it was a pleasure having you on. We can't wait to have you on again.
for sure.
And yeah, so I am your host, Parker.
And I am Ray, and we will see you soon.
See ya.
Yeah.